Hello, my name is Karthik Narayanan and I'm a student at University of Florida. And this is my project for the course Image Processing and Computer Vision. The title of my project is Analysis of Dual Stego Process in Improving the Embedded Capacity for an Image Steganography. We live in a digital world. Most, if not all, of our workspaces have been conquered by computers and the internet. The widespread and ease of access are both a boon and also a hindrance for our lifestyle. The electronic data is volatile and sensitive in nature, and thus security of information is essential. Image steganography is one such tool of information security which combats illegal and unauthorized access to data, destruction, modification, and misuse of data. Image steganography is the topic which is being covered in my project, and this actually deals with the new process of image steganography called dual steganography or dual stego, and also involves analysis of various steganographic methods which are being employed currently. The aim of my project is to improve the embedding capacity of an image and provide an imperceptible stegno image quality. This is achieved through a dual embedding process which supports high embedding capacity and also high security. This dual embedding process includes embedding data in both transform domain as well as in spatial domain. Introduction. Steganography is the art and science of writing hidden messages in such a way that no one apart from the sender and the intended recipient suspects the existence of the image, a form of security through obscurity. The main objective of steganography, apart from securing the data, also involves improving the embedding capacity and maintaining a good PSNR. Embedding which is done should not draw any attention, and the message, once embedded, should be reliable. The message which is being embedded into an image should be decoded only with the help of certain keys which are provided to the recipient by the sender, and hence we can say that this helps to hide data and transform coefficients. Now, the different techniques which are being applied for image steganography can be divided into two parts. One called transform domain and one called spatial domain. Transform domain includes different operations performed by wavelets or on wavelets such as discrete cosine transform, discrete wavelet transform, and integer wavelet transform. The second being the spatial domain. Now, spatial domain involves several processes which come under the category of meta-swapping, such as least significant bit substitution, pixel value difference, and statistic embedding process, statistic aware embedding. Now, all the processes which are named have their own advantages and disadvantages. Firstly, we would go through the advantages and disadvantages of spatial domain and then the processes in transform domain. Now, we take the example of least significant bit substitution because we are going to use this in the later part of it. A least significant bit substitution may, involves directly replacing the least significant bit of the pixel of an image with the secret message which is being provided. Now, this method is very easy to handle and thus has a lot of applications in the recent times. And there also have been a lot of tools built which mimic the least significant bit substitution method. The process has its disadvantages, which include the lack of quality and also robustness. The lack of quality arises when some changes are made to the embedded image. For example, if the embedded image is compressed, then since the pixel values have the values of least significant bit associated with it, the compression will distort the image completely, and hence no such operation is to be performed on the image, and thus it is not robust. In the different processes and transform domain include DCT, DWT, and IWT. The advantage of DCT is that it it has some control over the quality of data, and it is also robust, but the problem is its hiding capacity. It has very poor hiding capacity. DWT overcomes this but has a low PSNR and thus is disqualified. IWT on the other hand is better when compared to DCT and DWT. It has good hiding capacity, a good PSNR, but cannot is not as is not complete. Even it has many defects, and thus even that cannot be used completely for embedding the data. And thus we go for the process called dual steganography, wherein embedding is done both in transform domain and spatial domain. Now I just wanted to show you my program for the dual steganography process, and I would explain the steps which are taking place in the form of an algorithm. This is actually a big, I mean, it's a big algorithm, so and it would take some time. So let's run the file right now. So it's running currently. So this is the block diagram for the project which is under discussion. Now this is the embedding procedure which I will explain uh, in the following steps. Now let's start with algorithm. Now algorithm for embedding data. Uh, the first step is called pre-processing, which basically covers the first three parts here. An RGB bitmap image is taken as a cover image and is loaded into a 3D array. The histogram modification is applied to avoid overflow or underflow of the image. The cover image is then partitioned into non-overlapping 8 pixel by 8 pixel blocks for each R, G, and P channels. Now, in our current process, this is how the embedding is being done. In the first process of embedding, we only perform trans- perform the embedding process in transform domain for red and green channels, and we leave alone the blue channel. And then the red and green channels, which have been on which transform IWT has been performed in transform domain, are then subjected to the least significant bit substitution again. So there is an embedding process being done in the spatial domain. And then finally, on the final image is the outcome. And then finally, the embedding process in transform domain is performed to the blue channel. Now, as I said, integer coordinate transform is applied on each 8 cross 8 pixels of the R and G channels using the following equations. Step 5 involves calculation of hiding capacity. Hiding capacity is actually very important, which differentiates different image technographic processes which from each other. Hiding capacity is one of the main criteria in our project. We need a high hiding capacity. Now, then once we find the hiding capacity, then we embed the data in all three domains LH, HL, and HH by using the formula. These three domains are obtained from integer variable transform when we apply integer variable transform. Now, integer variable transform uh, gives these four bands, LH, HL, and HH, and but we perform embedding only in three subbands, the LH, HL, and HH, and leave alone the LL band because it is of low frequency. And if we make any modifications in the low frequency currently, it will distort the image, and hence we perform IWT, and hence we perform the embedding in only the three high frequency domains. Next, an inverse integer Fourier transform is applied on these 8x8 pixels, and then an optical pixel adjustment algorithm is used to minimize the error between the original coefficient and the altered value by checking the right next bit to the modified LSB so that the resultant change will be minimal. The above steps are performed on both R and G channels, basically the red and green channels. Then the embedding is done in spatial domain on red and green planes by using the method of swapping, and key 3 is generated. Now till now we have been working on key 1 and key 2. Key 1 being the embedding capacity L, key 2 being the IWT obtained after process 2, which is used to embed in the three high energy bands, namely the LH, HL, and HH planes. Now, when we implement spatial domain embedding on the red and green planes, after that we have to consider five cases. The five cases being on comparing the left and right planes, if the left pixel is greater than the right pixel, and if the message is 1, then there is no swapping. And the second case being if the left pixel is less than the right pixel and the message is 1, then swapping should be done. If the left pixel is greater than the right pixel and the message is 0, then no swapping. If the left pixel is less than the right pixel and the message is 0, then there is no swapping. And if they are same, then no embedding process is done. And once we are done with this, we get two matrices of R and G planes, which are of 512 plus 256 pixels. Now, plane these planes have data are made up of data 1 and 0. 1 represents whether swapping has been done, and 0 represents when no swapping has been done. Now we use these two planes to obtain our key 3. Key 3 being a combination of R and G planes, 512 cross 256 and 512 cross 252, which uses 512 cross 512, a two-dimensional matrix, all of zeros and ones. And then after this process, we perform a lossless data embedding technique. After this, an IWT is performed on the blue plane after dividing it into 8x8 non-overlapping blocks, and lossless LSB data embedding technique is embedded onto this plane using key 2. Inverse IWT is applied on each 8x8 blocks after embedding, and they are aligned in just to get the original form. Then we calculate the mean square error and the PSNR values so as to determine the quality of the precision. As you remember, the main emphasis in our project was made on the mean square error, on the PSNR values, the hiding capacity, and hence PSNR forms an important part. PSNR is calculated from the above formula. Now we go on to the results. These are the images, test images which are taken into consideration, and these are the images after the steganography is performed. As you can see, a 512 cross 512 image is taken as a test image, and we are obtaining a 3085 cross 2950 image due to embedding of data in it. So we can see the difference here. The next part will actually be covered in the second video.